Okay, so oxidation of alcohols is another organic reaction that you're supposed to be aware of. No mechanism is required for this, although there are some conditions that are important that you need to be aware of. So alcohols are commonly used as fuels, and when they're used as fuels, they undergo combustion. Now, they're not quite as efficient fuels as alkanes because they release a little bit less energy per mole, and that's because they already have some oxygen on them. By their very nature, being an alcohol means having a hydroxyl or an OH group on you. So they're already a little bit oxidized, which means net the delta H is smaller than when you burn alkanes. Combustion can also be considered as like a complete oxidation of the alcohol. And so meaning that the carbon chain gets totally destroyed and you end up producing carbon dioxide and water, which are the fully oxidized forms of carbon and hydrogen. However, this oxidation reaction that you need to know is a little bit different from just the combustion reaction. It's really just a partial oxidation that keeps the carbon chain intact as the carbon gets oxidized. And so you're going to produce compounds that have C to O bonds, or that's also referred to as a carbonyl group, but keeping the carbon chain intact. The oxidizing agents, which sometimes you'll see them in reactions as just O, that would mean like some oxidizing agent, a generic oxidizing agent. But specific oxidizing agents to know are dichromate 6 and manganate 7. So dichromate, the di tells you that there's 2 chromiums, and the 8 tells you that it's with oxygen, and the Vi tells you the oxidation state of the chromium, which is +6. Manganate 7 tells you that it's with oxygen and that the oxidation state on the manganese is +7. So these are both really strong oxidizing agents, and either one could be used to carry out the oxidation of the alcohols. Usually the one that you see in questions, however, is the dichromate. So this is really the more important oxidizing agent to remember by name and by formula. So what's going to happen in these reactions is that the bonds between the carbon and oxygen are going to replace bonds that were originally between carbon and hydrogen on the carbon atom that has the hydroxyl group. And I'll show what that means with a number of examples. This means that depending on the classification of the alcohol, whether it's primary, secondary, or tertiary, different products will be formed, and the oxidation can take place a different number of times. So if you have a primary alcohol, this carbon here is the carbon that we're going to care about. This is the carbon that's going to get oxidized, the one that is attached to the OH group. Notice there are 2 hydrogens sticking off of that carbon. And so that means this type of alcohol can get oxidized either once or twice. So if I just write in generic O to represent oxidation, if it gets oxidized once, one of those hydrogens is going to get kicked off, and we're going to add a new bond between carbon and oxygen here. So now we have 2 bonds from carbon to oxygen, and that matches one of the older definitions of oxidation, gaining bonds to oxygen. So you can oxidize a primary alcohol once and form an aldehyde, or you can then remove the second C to H bond and form a carboxylic acid. Notice now the carbon has 3 bonds to oxygen. So primary alcohols can be oxidized once or twice. If they're oxidized once, they form aldehydes. If they're oxidized twice, they form carboxylic acids. But really, I mean, the key thing to remember is just wherever the oxygen is, the carbon that it's on is still the carbon that's going to have the oxygen afterwards. The rest of the carbon chain is totally unaffected by this reaction, and you just kick off one H at a time and replace it with bonds to oxygen. First, make the double bond, and then you can add this hydroxyl group here. So if we use that same strategy here, secondary alcohols are going to only be able to get oxidized once because they have 1 hydrogen on this important carbon. And if we kick off that hydrogen and we replace it with a C to O bond, we end up here. There's that carbon. This is a skeleton way to draw the structure. And now it has 2 bonds to oxygen. And now we formed a ketone. And I'll just draw in these other guys that are missing from this structure. So when secondary alcohols get oxidized in this way, they always form ketones because by their nature, the secondary alcohols have an OH somewhere along the chain in between 2 other carbons. And so when the double bond forms, it's in between other carbons, and therefore it's a ketone. Tertiary alcohols, however, don't have any hydrogens sticking off of this carbon atom, and therefore they cannot react in this way. So primary alcohols can be oxidized once or twice, secondaries can be oxidized once, and tertiaries cannot be oxidized at all by this mechanism. The conditions to know is really all about the primary alcohols, because as we just said, they can be oxidized either into an aldehyde or a carboxylic acid, and that's not particularly useful if you're trying to make just one of those products. So you can imagine in industry, it would be important to only make one of the products. So if you just want to get the aldehyde and not the carboxylic acid, you use the process known as distillation. Distillation setup is shown right here. This is where the reaction is happening in this flask. And as the reaction happens, it's heated. And so some of the products end up vaporizing up here. The tube is bent, and so the gas starts to go down this glass tube, where now we have a condenser. It's the thing I showed you in class. The cold water is circulating around this tube, and that's going to cause the vapor to recondense and drip all the way down and be collected down here. Okay, so you end up with a product in this flask. Now, the thing that's going to boil off first is the thing with the lowest boiling point. So the reason why this is a useful technique is because alcohols have OH groups. They can do hydrogen bonding with their neighbors, but aldehydes don't have H enough. They don't have H directly bonded to O, so they only have dipole-dipole forces, which means that they have lower boiling points than alcohols. So if you set up a distillation apparatus, the first thing to vaporize, the first thing to boil off will always be the aldehyde. And so the aldehyde will go up, down the tube, and it will recondense, and you'll get only aldehyde in this container down here. So these questions are often tied in with questions about IMFs and identifying hydrogen bonding capable versus dipole-dipole forces, and therefore lower boiling points. Okay. Now, if you only want to obtain the carboxylic acid, then you should do heating under reflux, which I showed the other day for a different reaction. If you have the reaction happening here, as things condense, the condenser is set up vertically so that things recondense and fall back into the reaction mixture. It essentially keeps everything in the reaction mixture and allows them to be completely reacted, and in this case, completely oxidized. So in this case, it's not that you don't form the aldehyde, it's just that as the aldehyde boils off, it's forced to recondense back into the reaction container so that it can then be fully oxidized into the carboxylic acid. So those are the two different techniques, and you would be expected to know which goes with which. The other conditions I realized that I didn't type in is that both of these things need acid as a catalyst. These are redox reactions. You may recall that very often we said in redox reactions that we could use acid or H plus to help balance things out. And so the acid is acting as a catalyst. So another condition is that you need acid. So sometimes they say sulfuric acid to be really specific, but you can also just say they need acid or it needs to be acidified. So this is another condition necessary for any of these reactions. The secondary alcohols that we talked about, now they can only form the ketones, but sometimes in order to increase the speed of that, you would probably do it under reflux. That way, it would make sure that all of the secondary alcohol gets turned into the ketone. So reflux it might be mentioned in a question related to secondary alcohols as well, but usually these two conditions are just for the primary alcohols to distinguish between the two products. Last note about the oxidation reactions is that they involve a color change. The oxidizing agent, especially if you think about it as this dichromate ion, that agent gets reduced in the process of acting as an oxidizing agent. And this half equation is actually in the data booklet in table 24, all the electrode potentials. So it's written right here. This is the reduction half equation for these alcohol oxidation reactions. The alcohol gets oxidized, and the chromium +6 is what's getting reduced. It's getting reduced from a +6 form to a +3 form. And it's a transition metal. In that change of oxidation state, it goes from being an orange color to a green color. And so if you do reactions with primary and secondary alcohols, as they get oxidized, the reaction container is going to change color from orange to green. as you form the chromium 3+. However, if you do tertiary alcohols, they don't get oxidized by this reaction, and therefore there'd be no color change, and the reaction container would stay orange. And that is the oxidation reactions and the conditions in a nutshell.